Hello. Hi, everyone. It's very nice to see you. Yeah, for the nice invitation. Yeah, so it's my great pleasure to be here. Yeah, in the seminar to introduce our recent work about adaptive voltage control. Yeah, for power distribution systems. And we designed the controller to explicitly consider the impact from the rapid net load fluctuations and also the mitigation strategies. So the problems are motivated from the recent transition in power systems in both the power supply and demand side. So for the supply side, so we have the clean energy transition, where different states have set up a goal towards the renewable and the clean energy integration in the next few decades. Right. On the side of the demand, we have seen the significant increase of the power demand. So that is partly driven by electrification, such as replacing the gas-fired cars with electrical vehicles, and more recently, the surge of the power demand from data centers. So altogether, this have introduced much faster and more significant time variations on both the power supply and the demand side. For example, the left side figure shows the AI training load from the Microsoft data center. So you can see, they have very huge oscillations in just 150 seconds. And from the bottom to peak, these oscillations can range about, so even to tens or hundreds of megawatts. So that will be a very large fluctuations in very short time period. And similarly, the right side, that is power from the wind farm in Germany. So you can see they also have very large time varying oscillations and the fluctuations. So altogether, this makes maintaining the safe and efficient operation of power system to becoming more challenging. And one of the most important metrics for the safe operation of power system is the voltage. Right. So in this talk, I was specifically talk about the impact of the power So for the power system, the voltage area is 5% of its nominal value. However, the high variability from the renewables and the sudden changes in load can lead to very large voltage fluctuations. For example, if we have more power injections from like the solar PV from the wind turbines, the voltage may increase. If we have more load, the voltage may drop.
It's saying the volume is low,
higher volume.
so I'm not sure it's the setting or. I'm not pretty sure.
Deep is saying this online, so it's not us hearing, it's them hearing.
It's my.
Can you? Is it okay now, Deep, or?
I think it was noise.
Yeah, I can hear you guys right now.
Okay, all right.
Yes, then thank you. Right. And so if we have seen more load, then the voltage will drop, right? So now let's consider, if the system subject to this kind of the oscillations in the net load, like from the data center load, then this would be the voltage deviation signal we can see. So the voltage also subject to very huge fluctuations, and the voltage deviation can reach to 10%. So that is outside the safe region in this 5%, labeled in green. So because of that, we want to design the voltage control law to reduce the voltage deviations. And the voltage control law is commonly defined, to regulate the controllable power, especially the controllable reactive power, according to the voltage deviations. And this controllable power can come from some inverter-based resources like energy storage. Correspondingly, the control law defined by the RGB standards, like RGB 1547 standard, defined to regulate the reactive power linearly with the voltage deviation from 1 per unit. And we also have the variant of such control gain to regulate the reactive power, also incrementally regulate that according to the similar control law. However, one inherent assumption of this design is that the load changes very slowly throughout the time. So during the time horizon for control, we can envision the load as kind of being constant. But if we just directly apply this control law to the system with significant time variations of the load, so like the data center load we have seen, this would be the voltage performance we can see. So although in some sectors, the controller makes an effort to reduce the voltage deviation to 0, but every time when there's some shifting of the load, there are always very large voltage spikes and voltage violations. So that means, the conventional define of the voltage control law is actually less effective when the system is subject to this rapid load fluctuations. Now considering that, because we have increasing penetration of large data centers and also the renewable power sources, so it becomes actually more important for us to explicitly considering the time varying load renewables in our voltage control problem. However, design this control law under the time varying load and renewable is not so trivial because on one hand, it's not clear how should we model the time varying net load. So should we model them as just a white noise, or should we design some parametric function to model the net load? That is yet to be determined. And on the other hand, we are facing the distribution systems with only limited communication capabilities. And we also usually do not have the exact topology and parameter of system, and the underlying physical system themselves is nonlinear. So all of this added the complexity for us to design the control law when facing with the time varying load and the renewables. So to overcome these challenges in this talk, I want to introduce some of our recent works that enable it to adapt to the time varying load and the renewables, but still can be independent with the exact system information or topologies. So I will start from introducing a voltage control.
Just to clarify, so are you focusing on distribution level?
Right, that is distribution level voltage control.
Not transmission.
Yeah, right. I should clarify.
These are more like conventional data centers from the past.
Smaller data.
Right. So now the data center is more huge, especially because conventionally the data center loads may be steady, right? So now the AI training data centers, they have this like fluctuations we have introduced here. So that is that kind of new patterns introduced by modern data centers.
It's usually I think maybe I don't know if I'm being fair here, but I think like the new data centers with this specific type of a load maybe are not on that level of the network.
At higher voltage level.
Yeah, it's usually in the transmission system. Yeah.
Oh, okay.
But that's the setting. Yeah, that's the setting. It's fine.
Yeah, thank you. That's so
especially
that
the software part. The curve they are showing is I think it's maybe hybrid scale kind of data center. So usually this will connected to like I don't know, like 35 kilowatt kind of level transmission.
Yes.
It's not maybe not the distribution, but I'm sure that maybe some other medium-sized data center will still have this fluctuation. So yeah.
Right. Yeah. So as far as it looks like in Virginia for the data center alley, there are some data centers that connect to the distribution system. But that's true. So whether they have this like very large computing load can scale to this level, so that it need to be further checked. But for that level, so even if it's not like hundreds of megawatts, if that is like tens of megawatts connect to the distribution system, that still can cause this sort of the voltage issues and the voltage fluctuations. And that's a very important questions. And I believe for the control law introduced today, that may also have the potential, to be applied for the transmission system level control. And definitely happy to discuss more, after this talk. Right, and then for the outline, of the talk today, so we are start from introducing the voltage controller, with designed with switching reference to adapting to the AI training workload, and then for some kind of the primary load, that is partially predictable. I also introduced how we can leverage predictions in the voltage control through design and adaptive control. And last, I will address how we can cope with the nonlinearity in the underlying physical model of the system, but still using a data-driven approach to cope with the nonlinear power flow without depending on the exact model parameter informations. So let's start from the first part, that is the voltage control with switching reference for the AI training workloads. So that is a joint work with my PhD student Mingyuan with Trigger and Balsam from University of Washington and Yize from the University of Alberta. So now data centers are becoming a new major participant in the power systems. So the capacity from data centers are expected to be more than double from the current level in the next 5 years. So different from the conventional load, the data centers, they are more geographically concentrated in the sense that just about 250 data centers can consume roughly the same electricity as Boston. So when some of the data centers, they have very large fluctuations in their load, so that can become very large disturbance to the power grid. And one representative type of the load from data center, so that is the AI training workload, shown as here, which have very rapid fluctuations and very rapid ramps. And and for this synchronized pattern, so that actually comes from the way how the large AI model are trained. So because so the model is too large for a single device to handle that, then the training usually need to distribute it across many GPU racks and also require frequent communication to update their model parameters. So once the training begins, then we'll see the rapid power increase through this phase. But when the training of one epoch ends, then the GPUs need to come to the communication phase to communicating over their gradient and also do the checkpoint savings. Then in that phase, then we'll see the rapid power decrease. And such pattern will repeatedly, again and again, so during the training epochs. And depending on the size of the model, so such oscillations from bottom to peak can reach about even tens or even hundreds of megawatts in the system. Now, as we have discussed here, so shortly in the introduction, so if we apply this kind of the load with fast fluctuations to the system, then we can see that is a fluctuations of voltage with very large voltage variations. So in this work, we want to answer the question that how should we design a voltage controller to mitigate the voltage deviations resulting from the AI training load, but also can avoid us to use too excessive control effort in the system. So to answer the question, let's start look at what is the model for voltage control we are considering. So for the power distribution system, we have different nodes. Each node they have their voltage denoted in V. They have their net active power injection in P and their net reactive power injection in U. And the voltage is affected by the active power and active and reactive power across the whole network. And the relation is commonly modeled by this so-called Lindy's flow model here. And here, both V, P, and U, they are as a vector, just stacking all the local variables. And here, the R and X, they are system matrices corresponding to the topology or resistance or reactance of the system. And here, data, that is the model areas. So from the original nonlinear system model, to this Lindy's flow model. And for the last part of the talk, I will talk more explicitly about how to handle, or analyze the model areas.
Maybe a quick question. So what is the controllable variables? You're controlling the IBR or you're controlling what?
Right, that's a good question. I will quickly talk about that. Right, so essentially now our goal is to design the reactive power here to regulate to reduce the voltage deviations. And the reactive power, so they may come from the inverter-based resources like the energy storage, like the solar panels. And here, because for the distribution system, we may not have the wide area communication capability. So here we consider a local controller that will just regulate the set point for the reactive power from this inverter-based resources based on the local measurement of the voltage deviation. And one commonly utilized the controller in literature is to iteratively update the control action based on the voltage deviation from their reference value. So in each time steps. And here Ki is a linear control gain. But we just if we just apply so this controller for the system with the like AI training workload. So this this will be the performance of the voltage, which have very frequent oscillations and the fluctuations. But to understand why this is happening, so let's look at the abstraction of the data center load as this square waveform. And this is square waveform, so which the power have the high load when that is in the training phase, and will jump to the low load, when it will switch into the communication phase. And what the controller is doing is that in each of the phase, they have tried very hard to recover the voltage to its reference value, that is 1 per unit. But every time, when there is some shifting of the load between the phases, and that will result in the sudden voltage changes. And now, because for the controller design, the control action actually can only react to the voltage deviation in the previous time step. So after the step change, they can reduce the voltage deviation. But the largest step changes resulted from the load changes. So so that under this controller is actually not affected by the controller itself. Now it looks like if we cannot really predict exactly when the step change is happening, then it looks like under this current controller, we cannot do much more to further reduce the deviation, right? Because that is originally determined by the step changes of the load themselves. However, it is very interesting that it turns out that by a very simple design, but just changing the reference of voltage to be time varying with this shifting of the load, we can actually reduce the voltage deviation by half, but without incurring some extra control effort. To see this, let's just revise our controller here. So the only difference is that now the voltage reference, so it's a time varying reference instead of just a 1 per unit. And the key idea is that, so we cannot change so how large the voltage is like shifting, resulting from the step power changes, but through changing the reference, we can control the starting point from when the voltage, start to change. For example, so when that is in the training phase, that resulting in the voltage drop. So instead of set the voltage reference to 1, we set them to be half of the largest voltage step changes resulted from the power changes. So then when the power shift from the computing phase to the idle phase, right? So that is a sudden load decrease. So that resulted in the sudden voltage increase to the magnitude of delta V max here. But because we are starting from the point that is just the minus half of the delta V max. Then after the shifting, then it will just shift to the value that is about positive half of the delta V max. Then through the simple design of the delta V of the voltage reference, then we are able to successfully actually just reduce the voltage deviation by half, right? And especially, so here by setting up the reference properly, so in this example, so that is half of the magnitude of the delta V max. Then the voltage reference can follow exactly the trend of the voltage deviation term here. So that, under these circumstances, then the second part on the controlled adjustment term will just become 0, right? So then we just need actually very small effort, for the voltage regulation, but we can, reduce the voltage deviation by half compared with a conventional design that just set the voltage reference to just become 1 per unit. So that will be a kind of the improvement. So with a very simple adjustment on the voltage reference that can achieve,
Can I ask a question?
Sure.
So is this the reference? Is that based on the fluctuations that you're seeing on the P?
Oh, right. Yes.
So how are you designing the reference?
Right. That is an excellent question. I will talk about that very quickly here. So in the next 2 slides, right? So that's you. Then how should we shifting the reference? That is becoming a very important question, right? So to understand how we should shifting the reference, essentially we're shifting according to the observation of the largest voltage changes in the past period, right? But to understand that, so that will be more clear after we see the closed loop behavior of the system, right? So now if we combine the so the voltage dynamics and also combine with the controller, with the primary reference, then the closed loop system we can compactly write down into this kind of form. So here we can consider the voltage minus its reference as a new definition of the state variable in the system. And here the I minus xk is just the state transition matrices, so that align with the classical design of the voltage control.
Excuse me, are you saying that you change the reference and the voltage at the same rate?
Right.
That cannot be done.
So that's actually an interesting design here. So the voltage jump here, right? So the voltage jump here, so that is resulted from the sudden power changes. And now because we set up the V reference here according to the previous voltage, so that is something related to the notation. The V reference T minus 1 is not utilized to adjust the action in the T minus 1. That is utilized to adjust the action for UT. Right. So that is the key design here. So right after the step changes of the power, that step changes is resulted from the from the power changes. But in the next step, because we shift,
you have 2 time scales. The load changes a little slower and reference changes a little slower, and then you do control a little faster. I think you are using T for everything. That's my question.
Right. So that is T for everything, but because that is the iterative algorithm, right? So the way how we set up the V reference T minus 1, right? So that is V reference T minus 1 is utilized to set up the U for the time step T.
So are you saying, I am trying to understand, are you saying because the load changes so fast, I have to change the reference point and my voltage at the same rate? They will fight each other. I mean, I set the reference point and right away I want to be there, and how can that work from control point of view?
All right. So because the reference point is essentially 1 step later than the so the key point is that the voltage reference.
How big is the step?
The step here in our simulation that is 1 second.
And then 1 second delays everything, sorry. And the load changes in millisecond? What times, can you explain time scales in your setup?
Right. So for the load, I believe, if I remember correctly, that is a 10 millisecond. So
it's changing very fast. And
Right.
you are chasing the reference that very fast. And then, what did you say, it changes every second?
All right, so the control action is implemented every second. Right, but the key here is
Or you
that,
filter or something, I don't know.
right, so essentially the underlying load is time varying, right? So they always change every time. Our control action, we assume it cannot
Change that
implement
fast.
so fast. Right, that's true. So that
So
is
you are just sort of filtering out and still letting those oscillations in between the seconds still happen, right?
Oh, right, that's
the result. Okay, so you need some filter or something, I don't know.
Right, can consider that as a filter because we can only take one measurement of the voltage in 1 second.
Right, but if you don't put additional pass filter,
Right.
then you're going to see within 1 second, you're going to see these oscillations because you're not controlling anything.
Yeah.
It would be nice to clarify
Right.
how fast disturbances change. Maybe you have some plots, I don't know.
Right.
It's like if you're sampling something at 1 second, something that is happening at 10 milliseconds.
Right.
What is actually that you're controlling?
I think average over a second, it filters like AGC,
Yes,
but
precisely.
yes,
Yeah.
yeah.
Right.
So it's just going to smooth out over 1 second. We do that in power systems all the time, but you cannot claim that you are then polishing it every millisecond because you're not. The poll is too slow.
Right, yeah, so I can
So what Maria is saying that actually inside here, there's a 2 time scale kind of
There are
function.
more than two.
Yeah,
I
and
think.
more than 2, yeah. So maybe in your formulation, you need to kind of
Yeah.
find a way to express that, but
So
otherwise
the time
yeah.
scales.
Because then we have a t and tau, and then tau is lower than t, then people understand, okay, there's a 2 time scale
So
in
we
the
have
settings.
measurements, we have rate of changes, which load changes and reference points and voltages change. Four of them.
Right.
Yeah, okay.
Yeah, so essentially can consider that way, like.
Because I think people will, it will
Yeah,
be,
it's very confusing.
because fast changing the reference point is somehow a risky kind of behavior in the
Well,
stability.
the reference point loses its meaning.
Yeah, it's
Because
true.
reference point is supposed to be a little slower.
Yeah.
Yeah, but she said that there is a delay, but delay, what is one? What is the step? Millisecond, you said?
Right, for 1 step, that is millisecond.
So that's
So-
a measurement? No. What is 1 second?
Yeah, so for 1 second, that is the interval. So we implement 1 control action every 1 second. We also have 1 measurement of voltage every 1 second. So that is our current setting of the simulation.
Okay, so the voltages are measured every second after second.
Right.
And the load fluctuates in between, right?
Right, that's true, yeah.
And so the control response.
Right, so the control responds to the voltage measurement every second. Right, but so for the control measurement and the response, that is, have 1 point every 1 second.
Yeah, so here it's
Right,
not
for the
t minus 1, it's like t minus 100, maybe like that, if you consider.
Here, like
You
T-
delay.
Yeah, the
T is 1
delay, yeah.
second.
It's like a 0 order holder.
Oh, yeah, okay, so can consider the way, yeah. So T here, that is the time
It's
step.
not clear. Isn't the signal relatively slower? It's like between compute
Yeah.
and communication, you said, I think, right?
Right, yeah, we can consider this way. So I think perhaps this slide can be helpful. Right, so for the real world, the data center load, that is kind of this way, right? Then the time oscillation may be about like 10 milliseconds. That is this power profile. What we are doing is that we implement 1 control action, so every 1 second, so that is 1 action here, 1 action here, 1 action here, something like that. So there will be the oscillation, still have the oscillation of the load in between. But as long as we are reacting to the largest changes of the power, we can still keep the voltage. Yeah, so in some relatively good range. So that is a key point here.
Did you simulate that to show us closed loop response with your measurements?
Right, yeah.
You will have that later.
Right, that's it, yeah. So I do have the latency.
Okay.
Right.
No, you have, is this simulation or what is this?
All right, so that is the reading of the computing load, from the data center load.
So
that-
still the input disturbance, right? But we are interested in what happens with voltage.
Oh, right, that's, yeah, so I'll say that very quickly. And before that, perhaps we can first, to be more clear about how the switching reference is implemented. So essentially that's, if you look at the closed loop system, right? The closed loop system, yeah, so so the voltage deviation from their reference voltage, yeah, so they're affected by the step changes of their active power in this time. But also so the last one is about the changes of the voltage references. So here, so we can see for the step changes of the power, then they will incur the step changes of the voltage in the field and step. But here, if we can shifting our voltage reference then the gradient of the reference. So that enables us to achieve the convergence of the voltage to reference. And by contrast, for the conventional design, right, if we just keep the voltage reference to just be constant, then the green term it will just be zero. So then that term cannot just cancel the impact from the step voltage changes resulted from the step power changes. So then how the algorithm is implemented is essentially that, so now because
What is the delta?
So the data term is the model errors. Model error from the linear flow model to the original disk flow model of the system. Right, because here we use the linearize the disk flow model to model, so that is exactly the model error.
How do you get that?
So for the analysis, we are not dependent on the expected form of the error. So we're just taking into this error into account to analyze the convergence of the voltage. So for the convergence of voltage, so we can see the impact of this term here.
But you should have some assumption on data, right? Like bounded or something.
Right, exactly, yeah. We'll show the input to state stability, so we require the bounded errors for the bounded voltage relation. That is a nice question.
Thank you. Can I answer another question? So I'm just trying to understand the setup here. So here, since you are already considering the in this say flow models, then it should be as a grid side, right? And so but the inputs what we observe is the load fluctuation probably software side. And in this case, the voltage actually here is from, for example, substation, or where's the measurement point by assumption?
So that should be understood as a kind of voltage on the primary side of transformer. So
primary side.
For this.
And then the follow-up question is this voltage instantaneous, or it's actually the average?
Phasor or
For that model by linear flow, that could be understood as a kind of average voltage. Within some period. So that is time horizon for linear flow to model the voltage. So that's exactly the more finer time scale, within milliseconds. So then we require some power electronics side of modeling to model this impact. So that definitely some gap we want to fill. Right, then exactly, we want the shifting the voltage reference to cancel the impact from the sudden changes of load, right? But here, so although we cannot directly observe, so what is changes of loads, what is the matrix R here, but their impact is actually reflected in the step voltage changes in that time step. So then the implementation can be based on the measurement, saying that we first observe what is the largest step voltage change. So in the past time window that is long enough to cover one period. And then after we have get the measurement of the largest step voltage changes, then every time when we have the step voltage increase that is large enough, then we just set up the reference to become to become higher than half of the data we max. So here the bias can be just understand as 1 per unit for the conventional design of the voltage controller. And similarly, when we have seen a voltage sudden jump sudden decrease to some range, and then we just shift our voltage reference to half or to minus of the half of the curve. In the figure before. And exactly the voltage step changes so in the range between, then we just maintain the current setup of the voltage reference. And now note that so here so we update our voltage reference at time step t using the voltage measurement at the time step t, right? So that's the reason why we can actually set up the voltage reference to follow the trend of the VR here, and we use that to guide the change of the action in the next time step. Now, because of this design, then the whole design just based on the local measurement. And because we can first detect the step changes of the voltage deviation and then do the shifting of the voltage reference. So that does not depend on, we can exactly predict when the step changes will happen. So yeah, so then the flow design is just that based on the measurements. Even though we can have different like a period of the step, voltage changes and step power changes, the proposed controller can still adapt well to this practice. And we also show that the closed loop system achieve the input to state stable if we make sure K matrices that satisfy this that's inequality. So to be clear, the K is a diagonal matrix that's stacking all the linear control gain from all the controllers. So if we satisfy these conditions, then we can show the system is input to state stable, meaning that if the system have bounded the disturbances, then will have bounded the voltage deviations. And also the convergence of the voltage, we can show it satisfy this nice inequality. So here's the left side, so it's that essentially the deviation of the voltage from the reference value. And the right side, the first term, that is the deviation of the initial voltage from the reference value. And because the constant C2 here is smaller than 1, so this term will especially decay to 0 throughout the time step. So the other terms are the impact from the in-phase oscillations of the computing load and also from the model errors. Then as long as so this kind of the power oscillations and also the model errors, they are bounded, then they can lead to some impacts to the voltage deviations from their reference value. So now after we have this design, then we can also see their performances.
Can I have a question? So in the
this I cannot hear from.
Can you hear me?
Yeah, I cannot hear from you.
All right. So in the previous slide, can you briefly describe how this convergence would look like with existing stabilizing control without the changing reference?
So for that design without changing the reference, actually the difference would be so here the V reference will just become constant, right? So that just become 1. So the difference is that we can consider the B term here. So the B term here that involve the cancellation of this red part, also the green part, right? So through the cancellation. If we just set up constant voltage reference, then this whole term resulted from the step changes here. So that will become the disturbance. So the whole term will become the disturbance term. So that meaning that the whole disturbance here will be much higher than the constant one. So if we just implement the constant,
So my question is, I'm guessing the C3 will change. Is that it? Because it is still going to be bounded by max load change, right? Even there.
Right. That's right. That's the question. Right. They'll still be bounded, but because now the magnitude will be much higher than.
Yes. Oh.
Right. Then that will be much larger voltage.
But I thought D is a input, right? Is it not? The power oscillations of computing load.
Right. Under this notation, the D is just the power oscillations of in-phase oscillation, because for the step changes that already be cancelled by our controller design. But if we so you want to derive the convergence when the reference of 1 per unit, then the D should involve also the disturbance provided by the step power changes. So that
No, thank you. Okay, no, that makes sense. Thank you.
That's good. Thank you for the excellent question. Right. So now that we are ready, to do the case study. So when implement to implement that to the HV33 bus system, and here we connect the computing load from the data center to one node of the system. And here the computing load, we are generated from training 70 billion of the llama model on H200 GPU servers. Then for the following figures, that shows the dynamic performances under the constant voltage control and also switch reference control. The left side is the plot of the control action. The right side is the plot of the voltage deviation. From the 1 per unit. So now the voltage deviation is from 1 per unit. I have to clarify here. So you can see if we set up the constant voltage reference, right? The left side, that is a very large, constant, very large voltage. So control actions. But on the right side, we can still see very constant, fluctuations of the voltage and also very frequent voltage violations. So that's that align with our analysis before. And now if we design our switching voltage reference mechanism, then we can see there. So now the left side is our control action. So the control action only have kind of small control action every time when there's some switch of the phases. But yeah, in many long time, yes, not the change of contraction just 0. So and now we can constrain the voltage deviation to be within 5%. Yeah, we are safe range. So here, that shows that by just design a very simple switching mechanism of the voltage control. Yeah, so we are able to use very tiny control effort, but still, achieve the good performances in limiting the voltage violations. And also to be more clear, for the simulation here, then for the control action, that is like one control action, control point every 1 second. But for the simulation with the power oscillation, voltage oscillations in between, so that come from the oscillations of the load of about 10 milliseconds. So that is this time interval, reflected here.
And sorry, I think you covered this, but I just missed it. The voltage that's being plotted, is it the instantaneous or like sort of averaged voltage? Like your instantaneous measurement or your sort of like average over the last second?
So for the voltage plot, that is instantaneous voltage.
Okay.
Right.
But it's only measured every second, so in average.
I think that's also the question I had.
Yeah.
Oh, okay. Yes. Oh, yeah.
Yeah. Well, this is simulation, right? So that you can still compute that metric, but yeah.
But I think those simulations are very misleading. That's 500 seconds. If you zoom in, I would like to zoom in to see what happens in 2 seconds.
Okay, yeah, sure. Yeah. So we do have the zoom in version, so I can keep that offline. Yeah, to see more details if you are interested about that. Yeah.
Do you have a zoomed in version here? No?
Yeah, so I have something in my students document, but not directly in these slides. So I need to pull out the
So how are they different?
So for the zoom in version, just have a little bit more details. So the details will be, so we just see some oscillations in between. So to be clear, for the plot here, that is still the plot of like, so the time interval of every 10 milliseconds, right? So the plot here is aligned with simulation time interval. It's just for the control action, that the control action is implemented like every 1 second, right? So the plot here, the simulation is just a simulation every 10 milliseconds. So align with that original like resolution of the load. Right, but for the control action, we assume we cannot implement control action so frequently. So the control action is 1 second. Yeah, so I'm not sure whether I have makes it point clear. Yeah, so
this is a very different time scale than what you showed on load deviation. The one before.
I think what she's saying is that this is plotted at 10 milliseconds. It's just, of course, it's showing it over a long time.
What was the initial disturbance? The load was, I forgot, the big screen. What was the time scale there?
Oh,
when you started your talk, don't go back, but I just.
Less than a second lag.
What?
Less than a second.
1 second?
Less than a second, the peaks. The
Yeah.
peaks.
The time scale here is 500 seconds, so I can't follow the camera.
Yeah, it's quite hard to see what is happening.
Mm-hmm. You really need to zoom in.
Yes. So thank you for the nice suggestion. Yeah, so for the next time, when I do the presentation, I will definitely show more details. I think that is very helpful suggestions. Right. And now, so actually from this figure, so we can see a little bit more details about the power draw, from the data center load, something like that. Yeah, we'll have some oscillations in between in the phases. And but the key point for this slide is that so for just the switching the V reference, right, we can kind of reduce the voltage deviations compared with the baseline, but still this kind of the sudden voltage jump from this range is still be determined by the sudden step changes of the computing load themselves. Then if we want to further reduce the voltage deviation, then what they need is that we hope that the data center themselves or combined with some energy storage can do something on like slowing down the ramping from the computing load or smoothing out the data center load.
Can I ask a basic question?
Right.
Your relationship for voltage change, they depend on changes in P, in real power?
Right.
Is that true, or they depend on Q main or reactive power?
Right. So first I check my understanding. So are you meaning that whether the voltage is just kind of determined by the instant?
No. Well, there is the decoupling on real reactive power, right?
Oh, right. That's
so maybe on the distribution network, you can still say something about how voltage changes as a function of real power changes.
Yeah.
But not much.
Yeah, in your Lindis flow, like what is, you have 2 by 3 matrix, right, of your sensitivities, like what is affecting what?
Yeah. What depends significantly on what in the distribution network? Because in the whole power system is more like voltage really depends on Q imbalance. Or reactive power imbalance, but maybe distribution network is different.
Yeah, and I think another issue is I believe how when you please correct me if I'm wrong. So your recovery voltage is actually you first measure, for example, by NVIDIA SMI for the power consumption, right?
Right.
Okay, and then you use some kind of models to infer the voltage.
Right.
But here's actually like a missing part. So first, I think what is exactly what Maria just mentioned, the question. And second is actually because you actually want the voltage as the primary side of the substation or transformer. But it's actually like a couple of steps. So like first transformer from the grid, and then some like internal transformer, AC, DC, and DC to AC to DC again, step down from all the way from like the KVs to like, I think then a few hundred volts and essentially 48 volts. And then on the chip level, it's like 1 volt.
Right,
In
that's
the DC, so when you're trying to map the power from the DC side to the AC side that has a high voltage is kind of like a missing. We're trying to understand.
Yeah, totally agree. These are all excellent
Should read
questions.
my paper.
Right, so the question is related about the modeling of the voltage control problem, right? So what is the right modeling? So first, in terms of the R and X matrices, right? So for the distribution system, the R and X matrices come from actual resistance and reactance from the power line, right? Then like how sensitive they are to the like, active power or reactive power. So that's actually corresponding to the resistance and reactance of the power lines. And especially for the distribution system, because the resistance is more like significant than the transmission system. So they can incur much higher voltage fluctuations for the distribution system. Yeah, so that is one part from the modeling.
Different from bulk, you know.
Right, that's true. Yeah, but that's true for the distribution system. We also have different layer of the structure, right? We have also the transformer from the high voltage, to lower voltage. You have the type changer control of the transformer. So that's true. Yeah, how could we further incorporate this kind of different layer of the control layer into our stability analysis and the control? Yeah, this I believe are very important. Yeah, so next step of this work we need to do, right? But I believe this kind of the general idea of the like shifting the voltage reference, to reduce the voltage deviation with very minor control efforts. I believe this kind of design should
theoretically sound, or I've never seen it before. I adjust my rows around the bias and something works. What is the theoretical foundations for that control that you could work? Like you just change the reference point based on the bias, yeah. Where does that come from? Yeah. Did that come from machine learning or what?
All right. So that basically comes from our intuition.
Intuition only, but is it working?
So our intuition when analyzing, this kind of behavior, and why it works, that comes from this closed loop analysis.
Which analysis?
Oh yeah. So that is the analysis of this closed loop system behavior, consists of both the linkage flow we have here, and also the control action.
Sorry, but my question is how that changing that reference plus minus 1/2 the max, how is that affecting the controller,
Right.
Convergence of the controller or whatever. I just don't see the connection.
Oh, okay. Yes, and thank you. So I got the point. Right. So how that shifting that matters one. Yeah. So how we cancel
intuition, but it's not clear that theoretically, where does the theory come from?
Right. Yeah. So thank you. That is something I should clarify. Yeah. So the theory come from how we can cancel this, like the red term here and also the green term here. So the red term here, essentially that is the voltage jump, caused by the sudden power increase. So this PT plus 1 minus PT. So that is the sudden power increase across different time steps, right? 1 times R. So that essentially that is the sudden voltage resulted from the sudden power change. So now, for our algorithm, essentially this switch reference essentially makes the second term, the difference between the V reference at T plus 1 and minus V reference at T, making that equals exactly the heavy T plus 1. When we have the sudden power changes. Now, because through the design, we can exactly cancellation of this green and the red part. So that enables us to greatly reduce the impact from the sudden changes of power.
It looks like that last second term is more like model predictive because it's T plus 1. So the red you are changing in a feed-forward way because T plus 1 and your feedback is T minus Vref of t or t minus one. I don't know where t minus one got lost.
Oh, right. Yeah. So here T minus VIT minus T minus one. So that is the step voltage changes. So that's corresponding to this term.
But
So like
there is t plus one minus t. So it feeds forward. You're trying to cancel the predicted impact or predicted increase in p by changing the set point in a predictive way because it's t plus one, right?
Right. So thank you. That's a great point. I should clarify that. Right. So here the PT plus one minus PT. So that resulted in the voltage step changes in the step like VT plus one, right?
Do I know it that t what t plus one is going to be or it's predicted? What is it?
Oh yeah. So that is based on the measurement. So
the done ahead of time.
Right. Oh yeah. So we can do that because the other assumption that we have the periodic pattern. So we can at least so after we have seen one period of this voltage fluctuations.
So you assume stationarity. You assume stationarity or
right.
Okay.
Yeah. So we can consider this way. Yeah. So essentially there is a consideration. Yeah. So because if there is no periodic pattern of this step changes, then we cannot expect that they can always follow this trend, right? But for the AI training load, we can expect like within some long enough time period, their power consumption is kind of periodic, and where the step power changes that not change too much. So that is something we can say.
That
for this
assumption
AI
should be
computing
spelled out, I think, because
right. That's I forgot to mention that.
Okay.
Thank you so much for the pointing this very important point. Right. So here, we want to show that. So by further adding some control from energy storage to smooth out the data center power consumption, then we can So if combining with this impact, also let's change the period and the peak of the power, right? But because our implementation is based on the measurement of step voltage changes in the past period. So after the shifting of this kind of the load, from the data center, right after shifting, so our controller also incurs some control action. But after that, it also can adapt nicely to this shifting of different ranges of the step changes and the different period of the step changes. So that is kind of the benefit of the design of the controller. So where we just based on the measurement to do the switching and the design. So
can
that
I ask another question?
Oh, yeah, sure.
No, sorry. I know that he asked the question, but I didn't quite get it. Where do you measure voltage? At the point of contact after the step-up transformer, or where do you measure your voltage change?
Right. So that is the local voltage change.
Where?
So we have different nodes, right? That could be understood as the
but at that
primary.
node you have several layers. You said at which layer
I think
do you
it's a
measure?
PCC, Maria.
What?
It's a PCC. That's
Well,
the
if
point
it's
you
point
connect
of
to.
common contact, then that is all filtered out. You don't see any of these fluctuations because transformer filtered them out. So which rate are we chasing here?
Okay, so here we can imagine that as a node, like in the primary transformer side. So that is the side, so where the voltage is having the measurement.
So point of contact is secondary side of transformer.
Yeah.
So she says you measure it before. You measure it before you step up the transformer?
Right. So we could consider this way, like for the simulation.
That is much more fluctuating, but if after the transformer there's no problem. So which problem are we actually trying to fix? That these fluctuations in load are not causing voltage deviations at the point of contact or before? What are we trying to fix with this control?
Right. So for this control, for this kind of design, we can consider them as kind of the so the distribution system modeling to the stage of the primary transformer side. Not because when their data center connection has fluctuation of the load, they still will affect the voltage on the primary side, right? And the fluctuation from the primary side will still transferred to the secondary side. So they do have this relation.
Still trying to fix what's happening on the grid side, right?
Right. That's right. So essentially, the voltage here is a grid voltage.
No, Mary. I think here this load is DC load. Is power.
Yeah.
And then what you're saying is the total power for the load. And then what you're saying filter out the harmonics. So you think about this DC load will change to some AC, and the AC You can think of the AC magnitude is changing. So this is showing actually the magnitude is changing.
No, the time constant on transformers go much slower
Yeah,
than
it's slower.
AC. So it filters out a lot of stuff. So I don't know which.
I don't think she's modeling the harmonic, so it's okay. It's mostly the phasor model. So,
Millisecond.
yeah, kind of like that. It's mostly 60 hertz, so it doesn't consider the harmonic, so it's okay.
No, I'm not talking about harmonics. I'm talking about little oscillations and the millisecond.
Yeah, so there's still some content, but I think it's fine.
I'm
Just finish
sorry.
the first. Yeah.
But this is interesting topic, you know, so, okay, keep going, sorry.
Yeah. Thank you so much. Yeah, there are a lot of very nice discussions. I think it's true. Yeah, for our modeling side. Yeah, so we do need to so consider a lot of more higher fidelity version of the model to make that to be more realistic, align better with the real world power grid. So I do agree with this point. Right. So now we are close to finish the first part for the talk. So essentially, for this part, so we introduce how we can reduce the voltage fluctuations by introducing some like simple design of switching the voltage reference, right? So this can avoid us to using excessive control effort and also guarantee the input to state stability of the system. And for some future directions, so let's choose on one hand that is so we should pick more high fidelity modeling on both the power grid side and also the data center side. And also data center, for one system, distribution system, we have multiple data centers. If each data center, they have these step changes, then the impact may overlap with each other. Then we need further check how we should decide for these cases and whether the performance guarantees still hold. And in addition, for the convergence analysis, we also have not included the both under interactions and also similar, for the time scale deviations between the control action implementation and also the original time varying load. So these are all need to be fixed in the future research. So that essentially, we complete the first part of the talk. I think I can very briefly talk about what we are going on in the next part of talk. And I think I will also update the slides and also the reference paper for this, the rest of the talk. So if you have any you are interested about, feel free to check that. And if you have any questions regarding that, I'm also happy to schedule another meeting to talk about that. So essentially for the first part, we talked about the time varying load, this kind of AI training data center load that have extreme fluctuations, right? But there are also different kind of the time varying load, like from the measurement of the Caltech campus, we have this different time varying load from different location of the campus, and like from the renewables, we also have like different type of time varying load. They are still time varying, have fluctuations, but not so extreme, than the data center load. And especially, from the slopes, there might be some patterns we actually can predict. So for the next part of talk, I actually will discuss. For this kind of more general time varying loads, if they are partially predictable, then how can we embed predictions into the controller, and how can we achieve the performance guarantees under the prediction error by combining the design of the adaptive controller with the prediction. So that will be the second part of the talk. And for the last part of the talk, so that will be related about how can we handle the nonlinearity of the optimal power flow problem. So for the nonlinearity, so essentially the reason is that even for the disk flow model, for the distribution network, the original model they're actually so this sort of disk flow model, then the linked flow model is essentially the linearization over the flat operating point. Then how to cope with the nonlinearity in the system, and also cope with that when we do not know the exact topology or parameter of system, then we propose the successive linearization approach. Here, we can do the data-driven successive linearization to gradually adapt to the current operating points, and we can still achieve some like guarantees on the convergence to the KKT point. For the original control problem with this nonlinear and non-convex, this flow constraints. But also to be more clear for the last part of work, that is just something we try to cope with nonlinear version model. So for now, this design still needs some communication capability. And in the next step, we want to extend, for this work to be implemented when we have a limited communication infrastructure. So that will be the major part of the risk parts of the talk. And for the next two parts, so actually the content can be found in these two papers, in these references. And if you have any questions, about either the first talk or topic of the talk or the later part of the talk, feel free to reach out to me through this email. So thank you again for all these very useful suggestions and insightful discussions. And I'm also happy to handle the other questions.
I would like to make a general comment coming from, maybe older generation.
Yeah.
I think these proposed new controls with adaptive and machine learning have to be put in context of how is wind power control working now? What is state of art? You have 4 types of wind controllers. Some control voltage, some don't, and whatever.
Right.
So something works now, it's already in the field,
Right.
in particular with wind.
Right.
There's a lot of good stuff that works.
Right.
So what are we improving? I think just to put it in context of, it's not just linearization, it's not just Caltech, distribution flow or whatever. It's just solve some problem that we can't solve otherwise. And I would like to understand that better. How is the adaptive? And give me one challenge problem that I can't solve the way state of art is now.
Right.
For example, I have a big problem with linearization when I have these big jumps in load.
Right.
So even successive linearization won't work. So I
Right.
may need to have some very clever feedback linearizing control or
Right.
sliding mode control or something that is actually going to work
Right.
under those big jumps. So there are a lot of assumptions here. And some of even state of art doesn't work because of those assumptions. So which assumptions are we relaxing here to actually solve something that we otherwise don't know how to solve? That would help a lot.
Yeah,
You
yeah,
are
thank you so
doing
much. It's very
distribution factor
insightful.
distribution control. What are you doing with the river now?
Oh, OPF.
What is that OPF can solve that?
Like it's OPF in the context of virtual power plants. Like it's not control dynamic stuff at all.
No, I understand, but what is that people can't do? If you were to solve yours on the distribution network, what problem would it solve?
I'm happy to
Real
take
world
offline. Let's talk about which.
I'm making a very general,
Very nice
general
question.
comment to people just starting from
Yeah,
like
no.
nothing was done before.
No, I understand, but I'm happy to dig it. But I understand the general comment. I just want to focus the specific questions on the speaker.
Right. Yeah. Right. Yeah.
I don't have any more questions.
So, can I ask a question? So, this is not my area, so it's maybe a stupid question, but so you're basically showing a simulation results
Right.
entirely, right? So,
Right.
and to demonstrate that this actually works, the next step be to test this out in the lab somewhere.
Right, that's you. Yeah, so for this control, when we want to directly deploy in the real power grids, that really will be challenging, right? Yeah, so I would envision for the next step is that if we have the kind of the hardware in the loop